Hello everyone, in this paper we present an end-to-end optimized video compression framework for the P-frame compression challenge in CLIC 2020. Existing works for learned video compression are usually based on optical flow networks and pixel residual coding. However, we notice that the pixel space residual is sensitive to the prediction errors of optical flow. Let's look at an example. The large residual in red box is almost the pixel value differences between the moving object and background. A similar case happens in the occlusion area as shown in green box. We aim to design a robust residual compression module to decrease the aforementioned influence on residual information. Let's start with the overall coding pipeline of our P-frame compression framework. Firstly, the reference frame and target frame are fed to the motion estimation network to generate optical flow field. We employ the optical flow network PWC-net as our motion estimation module. Then the optical flow is encoded and decoded by the motion compression network. The corresponding bit stream is transmitted to the decoder side. Here we implement an autoencoder-based network with a factorized entropy model. With the aid of decoded optical flow, the motion compensation module first warps the reference frame to target frame, and then refines the warped frame using a U-net lag network. The output of this module is the compensation frame. Later, given the compensation frame, the residual compression network aims to capture the remaining spatial redundancy in target frame. Following recent works for learned image compression, we implement an autoencoder-based network with hierarchical priors to compress residual information. The corresponding bit stream is also transmitted to the decoder side. Finally, a post-processing module is employed for quality enhancement to get the reconstruction. We use the grouped residual dense network as our post-processing module. So the total bitstream meaning contains two parts, one for optical flow and one for residual. In this paper, we focus on improving the performance of residual coding. To suppress the influence of motion compensation error, we propose to compute and compress the residual in feature space instead of in pixel space. Part A is the commonly used pixel-level residual coding method. Part B is the proposed method. We first encode both the compensation frame and target frame into feature representation. Then the corresponding feature residual is compressed by an autoencoder-based network. The feature representation is more robust to the prediction errors of optic flow, leading to more compressible residual. This figure shows the detailed structure of our feature residual compression method. The residual information is calculated in 2 times downscaled feature space. We use a shared feature encoder to extract the feature of both compensation frame and target frame. The feature encoder contains a downsampling layer and the residual blocks, which is very lightweight. The quantized latent M hat is modeled using Gaussian mixture model, and the hyperlatent Z hat is modeled using the factorized entropy model. Apart from that, we propose a step-by-step strategy to improve training efficiency. In the first step, we keep the width of the pre-trained optical flow network fixed, and we optimize the motion compression and motion compensation networks by minimizing the rate distortion loss of the compensation frame. Then the residual compression module is added for joint training, as shown in step 2. Finally, we add the pre-trained post-processing network and fine-tune the whole framework using the overall rate distortion loss. The rate of optical flow and residual is estimated by the entropy models. The distortion is measured using multi-scale SSIM. The evaluation results on CLIC p-frame validation dataset are shown in the table. Each model contains two submodels trained with different lambda. Given the target file size, a knapsack solver is used to perform bit location among the frames in validation dataset. GRDN is our post-processing network. We can observe that GRDN improves the performance of the model with pixel residual coding, but the decoder size is increased by about 50%. It can be also observed that our feature residual coding brings significant performance gain with a slight increase in decoder size. Compared with GRDN, our proposed method is more efficient and more lightweight. And the performance gain of GRDN is rather small on the model with feature residual coding, which demonstrates the effectiveness of our residual coding method. Moreover, we ensemble two submodels, one with pixel residual coding and one with feature residual coding. The ensemble modeling further improves the performance, as shown in the Model 5 and Model 6. Due to time reason, we only submit the version of Model 5 for CLIC computation. Our team name is IMCL-MSSIM, and our workshop poster ID is 5. In the future, finding an end-to-end structure to jointly combine the advantages of pixel-level and feature-level residuals would be an interesting direction. In our recent work for learned video compression, our low-delay video codec outperforms the versatile video coding standard on HEVC Class B dataset when evaluated using multi-scale SSIM in RGB color space. Thank you for your attention.